Okay, so if you look at this first example, we have a particular reaction that we don't know the delta H value of. Okay, and then you're also given two other reactions that you do know the delta H value of. And so your goal is to make these two reactions add together to equal this top reaction so that then you can find its delta H value. So all you have to do is go step by step through each reactant and product in this overall reaction. So the first thing you see is 2S, so you look for S within these steps. Okay, so you see it right here. The only thing that's different is that this needs to have a 2 in front of it, and so therefore I know that I have to multiply this entire reaction by 2. Okay, and so in doing that, everything gets multiplied by 2, including your delta H value. So this is your new delta H value for that reaction. Okay, so now this reaction is basically crossed out, and this is your new one. The next compound is 3O2. O2 appears twice, so we're actually going to ignore it because it can be difficult to see how to manipulate the equation based on that. So we're going to move on to the 2SO3. SO3 only appears once. It's on the reactant side in the second equation, but it needs to be on the product side. So therefore, I need to reverse the second reaction, which means that my delta H value gets negated. Okay, so now that I've worked my way through all of the compounds in the overall reaction, I'm going to go ahead and add together the two steps that I'm given and see if they add together to equal the overall. Okay, so when I do that, the cancel and you're left with this equation at the bottom, which of course matches the one that you were supposed to find the delta H value of. So then you know that you can go ahead and add together delta H values for the reactions, and that will give you the delta H of your overall reaction. Okay, so if you move on to the next page, there are two examples of Hess's law problems. So go ahead and pause your screencast and figure out what the delta H values are for the two reactions that you're given. Okay, so for the first one, you should get delta H equals negative 196 kilojoules. And then for the second one, you should get delta H equals negative 474 kilojoules. Okay, and of course, these reactions can look more or less complicated, and you can also be given more than one step. Okay, you can have to multiply by a fraction, that sort of thing. Okay, so standard enthalpies of formation are pretty straightforward. Basically, an enthalpy of formation just means that we are forming one product. So it is enthalpy required to form, in this case, nitrogen dioxide. Okay. So every element in its standard state is exactly 0. That's just because it's the way it naturally exists. Okay, so you don't, there's no extra energy required in order to make something that already exists. It has to be in its standard state. You can use enthalpies of formation for each individual compound in a formula in order to calculate the enthalpy of an overall reaction. Okay, so let's say you wanted to calculate delta H of reaction for this reaction here, and you're given these two smaller equations at the bottom. You could basically treat this like a regular Hess's law problem, so you would need H2O, okay, and I need it to be on the reactant side, so I would reverse this reaction, and then this would become a positive 21, and then I'm looking for 4 on the reactant side, ignore the F2, and actually move on to the hydrofluoric acid. So that's on the product side, and you multiply this by 2, and the 6 is on the correct side. So I should just be able to add all of those together, and they will give me the proper enthalpy. Okay, so basically the steps that you're given are enthalpies of formation, and you can just treat it like a regular Hess's law problem. And so indeed, when you add those together, you should get negative 1,745 kilojoules as your answer. Okay? So this is the longer way of doing these problems. There's actually an easier way to think of it. So what you're basically doing, for reaction, you're taking the sum of the product minus reactants, and each product or reactant is multiplied by its coefficient. So if you look at the reaction from above, okay, remember that the formula was H2S plus 4F2 yields 2HF plus SF6. Okay, and then we said that this was negative 1,220 kilojoules. Delta H of formation here was negative 273 kilojoules. Okay, F2 is in its standard state, so this is just a 0. And then H2S is negative 21 kilojoules. Okay, so all we have to do to figure out the delta H of the reaction that we're given is to do the products minus reactants. So I multiplied 2 times this HF value because there's a coefficient of 2, and then I add to that the negative 1,220, so all of that goes in brackets, and you add those two values together, and then you subtract the reactants, which have each been multiplied by their coefficients. Okay? So if you look at this in-class problem, you're given a reaction, you're given enthalpies of formation for each of the reactants and products. Okay, and so when you work this out, okay, you should end up getting negative 891 kilojoules. Okay, so remember it's products minus reactants, so equals, okay, we'll leave off the plus 2 times the enthalpy of okay, and then I'm subtracting the reactants. So CH4 is negative 75 plus O2, which is just 0. Okay, and so that should end up giving you negative 891 kilojoules. Okay, so take a moment to go ahead and solve the next reaction composite screencast, and you should get negative 1,126 kilojoules as your answer there. Okay, so we're almost done. We're going to go ahead and move on to the next problem. And it says, which of the following will have standard heats of formation equal to 0? So remember, it needs to be an element in their standard state. So take a moment and think about what they'll be. Okay, so bromine and hydrogen are the only two that are elements and in their standard state. So these don't count because they're compounds. And mercury as a solid doesn't count because mercury should be a liquid in its standard state. Okay, and then what we have at the bottom is actually just a summary of what we've already talked about. So if you reverse a reaction, then the magnitude of delta H remains the same, but you negate it. Okay, if you multiply the equation by an integer, the delta H also gets multiplied by that integer. Okay, and then given that you have the enthalpies of formation, okay, you can just do delta H of the products minus that of the reactants, multiplying each compound by its coefficient. Okay, and then elements in their standard state are not included because their value is just 0. And that is it for Chapter 6. So we'll move on to Chapter 16 next, which will begin in class.